So to start off section 4.2, 4.2 is all about the second derivative test. We introduced in section 4.1's videos the first derivative test. The difference between the two is that the first derivative test is completely accurate, but a lot slower. The second derivative test, while still being accurate, sometimes won't end up giving us an answer. It'll leave us without knowing whether or not we can find a maximum or minimum. So it's faster, but not as precise. So it is useful to know both of them, and we'll be going through this just like we did with the first derivative test. To start off, we are first going to introduce what a second derivative is. So we have this definition that says, let f double prime of x represent the second derivative of f of x and the derivative of f prime of x. In other words, that's saying if you take the function f of x and you find its derivative, you get f prime of x, which is what we've been working with for quite some time now. But if you take the derivative of f prime of x, you will get f double prime of x, the derivative of your derivative. It might sound odd, but it literally just ends up being one more step using all the same derivative rules that we've been working with. From here, we have a theorem that says if f double prime of x is greater than 0 for all x on some interval a to b, then f is concave upward on that interval a to b. And if f double prime of x is less than 0 on that interval, then the original function f is concave downward on that interval. And I've drawn two graphs to demonstrate what each of these means. So concave upward is just another way of saying the graph looks like it's smiling. If you notice from this value x equals a to this value x equals b, so these are the intervals we're talking about, the graph appears to be smiling. That means it's concave upward. So this is what the graph would look like if the second derivative was positive throughout this interval. Likewise, concave downward means the exact opposite. Instead of smiling, it's frowning. From x equals a to x equals b on this graph, it's kind of drawn a little bit small, but this is our a value, this is our b value. Notice that the graph is now frowning. So this means that the second derivative is negative between a and b. So just like we used partition numbers to decide where the graph was increasing and decreasing in section 4.1, we will partition the second derivative to decide where it's concave up and concave down in section 4.2. And just like increasing and decreasing led us to maximums and minimums, concave up and concave down will in fact do the exact same thing, with a little bit more rigorous definitions to go with it. So from here, we're going to try an example. We have f of x equals x plus 1 over x. And we want to find where the function f is concave up and concave down. In order to do this, just like when we dealt with partition numbers, we would find the first derivative and set the top and bottom of its fraction equal to 0. We're going to do the exact same thing, but with the second derivative. It's the exact same process, but using the second derivative instead. So we will start by finding f prime of x. In order to find the derivative of x, we're just left with 1. Remember, the derivative of anything times x is just that number. Any constant times x is just that number. And there's technically a 1 being multiplied to this x. The derivative of 1 over x is a little bit more complicated. Unless you want to use the quotient rule, then it would help to rewrite this original problem. So we're going to change this to x plus x to the negative first power. Remember, we can move this x up to the numerator and give it a negative exponent. And now that we've done that, the derivative is much easier to do. It's just the derivative of x to the negative first. Remember, you multiply the exponent out front and then subtract 1 from it. So that gives us minus 1 times x to the negative 2, which just gives us 1 minus x to the negative 2. That's our first derivative. We now need to find the second derivative. So we take the derivative of these two terms. The derivative of 1, well, the derivative of any constant is always 0. And then the derivative of minus x to the negative 2, again, we multiply the exponent out front and subtract 1 from it. That gives us negative 2 times a negative is positive 2 times x to the negative third. And at this point, now that we're done taking our derivatives, we're going to rewrite this without negative exponents and simplified. So the 0 just goes away and we're left with 2 over x cubed because the negative exponent will move down to the denominator. Notice the 2 does not have a negative exponent. That's why it stays right in the top in the numerator. Now we need to find our partition numbers of the second derivative. And just like we used to, we are going to take the numerator and denominator and set them equal to 0. So 2 and x cubed each equal to 0. Nothing can make 2 equal to 0, so there aren't any partition numbers for the numerator. But remember, as we discussed in section 4.1, if you have anything, any factor being raised to the second, third, fourth, fifth power, it doesn't matter. If it's equal to 0, then that exponent can just be taken away. It has no effect. You could also take the cube root of each side if you really wanted to. And it would be the same thing as just saying x equals 0. Again, that original cube or third power has no effect. So, our only partition number is x equals 0. So that's the only value we have to check around in a table or number line. In section 4.1, I did a lot of examples with tables, so I'm going to do a number line for this one. We're testing around x equals 0. So testing a number to the left and right of that, we'll just test -1 and +1. But remember, we're not plugging them into the first derivative now. We're testing for concavity, which means we need to plug them into the second derivative. So when we plug -1 into the second derivative, 2 over x cubed, we get 2 over -1 cubed, which gives us 2 over -1, which is just -2. And all we care about is that that result is negative. When we plug 0 into the second derivative, we get 2 over 0 cubed, which is undefined. Anything divided by 0 is undefined. And finally, if we plug 1 into 2 over x cubed, we get 2 over 1 cubed, which just leaves us with 2, which is positive. So with that in mind, we know that f double prime is greater than 0. Let me write it like this just to make it more comfortable to how we normally write this. F double prime of x is greater than 0 for all x in what interval? So for all x in, let's see, we said in this number line, f double prime is positive for every number to the right of 0. So we'll say for all x in the interval 0 all the way to infinity, since every number to the right of 0 will give a positive second derivative. And now from there, f double prime of x is less than 0 for all x in, and now the interval where f double prime is negative is from 0 all the way to the left, which means starting at negative infinity and working all the way until this 0 where the second derivative becomes undefined. So we put 0 parenthesis. Remember, you will never use brackets for these intervals describing increasing and decreasing and concave up and down. So, from our definition that we just introduced at the beginning of this video, we can say that f is concave up, or concave upward, on the interval where f double prime is positive or greater than 0. So f is concave up on the interval 0 to infinity. And from there we say f is concave down, or concave downward, on the interval where f double prime is less than 0, which we said was negative infinity to 0. And now we know everywhere that the graph is concave up and everywhere that it's concave down. So if you were to draw this graph on a calculator, essentially you would see, it might not be as easy to see as the parabola examples we showed at the beginning of this video, but essentially to the right side of your graph, so from 0 to infinity, the graph will look like it's smiling because it's concave up, and then on the left side of your graph, all the way up until x equals 0, the graph will look like it's frowning because it's concave down. Okay, so to finish this first part of section 4.2, I want you all to try this last problem. We have f of x equals x cubed minus 3x squared minus 24x plus 32. I want you to go ahead and find where this is concave up and concave down. Take a moment to pause the video and try this out. Okay, so from here, remember the first thing we have to do is partition the second derivative, so we have to find f prime of x and f double prime of x. So finding f prime of x, we take the derivative of x cubed, so we multiply the 3 out front and subtract 1 from it. That gives us 3x squared. The derivative of minus 3x squared, well again, we multiply the 2 out front and subtract 1 from it. That gives us minus 6x. The derivative of minus 24x, the x is just going to go away, leaving us with minus 24. And the derivative of 32, well, the derivative of any constant is just 0, so that goes away, giving us 3x squared minus 6x minus 24. And now, again, we take our derivative. The derivative of 3x squared, we multiply the 2 out front and subtract 1. That gives us 6x. The derivative of minus 6x is just minus 6. And the derivative of minus 24 is again just 0 because it's a constant. So now that we've taken our second derivative, we partition it by setting it equal to 0. It doesn't have a fraction, so we just set the value we have equal to 0. There isn't a denominator to set equal to 0. Solving for x, we'll add 6 to each side, which gives us 6x equals 6. And then dividing each side by 6, we get x equals 1. So this is our partition number for f double prime of x. This is the only location where the graph could change concavity. So once we test to the left and right of this value, we'll know everywhere where the graph is concave up or concave down. So for this problem, we'll go ahead and use a table. Again, you could use a number line if you prefer. We're testing x and f double prime of x. So we take our value of 1 and we test a number to the left and right of it. So I'm going to test 0 and 2. When we plug in 1, we know that f double prime will equal 0 because that's the value we got from setting f double prime of x equal to 0. When we plug in 0 into 6x minus 6, we get 6 times 0 minus 6. That leaves us with negative 6. All we care about is that is a negative value. And from here, we plug in 2 into our second derivative, which gives us 6 times 2 minus 6, which, when we simplify that, gives us positive 6. All we care about is, again, that this is positive. So from here, we can say that f is concave up and f is concave down on what intervals? Well, where is it concave up? That's everywhere that the second derivative is positive. So that starts when x equals 1 and goes all the way until positive infinity. So that's from 1 to infinity. And then where is f concave down? Well, that's everywhere the second derivative is negative. So that starts all the way at negative infinity and stops at 1. So we say negative infinity all the way to positive 1. And this is everywhere that the graph is concave up or concave down.